welcome back. In this lecture we are going to understand the sizing of electric vehicle powertrain and learn how to estimate the forces on the vehicle and the power that needs to be delivered by the powertrain to control the vehicle speed. There are three learning objectives of this lecture. First, what are the forces acting on the vehicle when it's driving, namely the rolling resistance force, the aerodynamic drag force, and the gradient force. Let us start by analyzing the rolling resistance force. The rolling resistance force occurs due to the friction between the tires and the driving surface. The rolling resistance force is zero at standstill. When the vehicle starts moving, the rolling resistance force acts in direction opposite to direction of motion and can be calculated by the rolling resistance coefficient CR multiplied by the normal force between the vehicle and the road. For a flat surface, the normal force is the vehicle mass m times the standard of gravity g. In case of road with inclination angle theta, the normal force comes the weight mg multiplied by the cosines of the road angle. It is important to note that the rolling resistance force is independent of the vehicle speed and it is always opposite the driving direction. The coefficient CR should be low as to keep the friction losses low. For modern cars, it's typically around 0.01 to 0.02. As the vehicle speed increases, the aerodynamic drag force opposes the vehicle motion as it forces the flow around the moving vehicle. It can be calculated as the product of the aerodynamic coefficient CD, the frontal area vehicle AF, the air density ρ, and the square of the vehicle speed V, all divided by 2. It is hence important to note that the aerodynamic drag is independent of the vehicle mass and has a strong dependence on the vehicle speed. That is why in car the aerodynamic drag force is higher than rolling resistance force when the speed is above about 70 to 80 km per hour. Secondly, the coefficient of drag is typically around 0.25 to 0.35 for modern cars. SUVs with their typical boxy shapes have coefficients in the range of 0.35 to 0.45. The third force that acts on the vehicle is the gradient force and occurs when the vehicle is driving on uphill or a downhill road. The gradient force is due to longitudinal component of gravitational force, namely mg sine theta, where theta is the inclination angle of the road as seen earlier. The cosine components mg cosine theta contributes to normal force and corresponding rolling resistance force. The gradient force and the angle theta are negative when driving downhill and positive when driving uphill. Road gradients are expressed as a percentage in terms of tangent theta and have a value typically between plus or minus 10%. If we now consider a vehicle moving on an inclined surface, then the aerodynamic drag force, the rolling resistance force, and the gradient force act on the vehicle. If we now include the traction force provided by the vehicle powertrain, then the net force on the vehicle F net is the difference between the traction force and the sum of the forces due to the aerodynamic drag, the rolling resistance, and the road gradient. By Newton's second law, the net force is equal to the product of the vehicle mass and the vehicle acceleration. Therefore, we can control the vehicle acceleration and thereby the speed by controlling the traction force that the powertrain produces. The traction force is the driving direction most of the time, but it can be zero when the vehicle is coasting or even negative when the powertrain is under regenerative braking. If we now expand the equation for the traction force, we can see the factors that influence the vehicle forces. The vehicle mass and the road angle affects the rolling resistance and gradient force. Vehicle speed decides the aerodynamic drag force, and the rest of the traction force decides the vehicle acceleration. If we need to estimate the power delivered by the powertrain be tracked, then we need to multiply the traction force if tracked with the speed of the vehicle, v. It is important to realize that in this lecture, we only take into account the forces in the forward and reverse direction as they influence the powertrain. The forces in other directions are neglected for simplicity. Secondly, the forces in the vehicle are assumed to be acting at one point. In reality, the forces are distributed over the vehicle. To conclude, the forces acting on the vehicle when it's driving consist on the rolling resistance force, the aerodynamic drag force, and the gradient force. The drivetrain provides the traction force, which can be controlled by changing the vehicle acceleration and hence the speed.